4 or 5 months now, and we very recently got some very amazing results towards the goal of building some kind of reasoning, as it has come to be called, in small models. And a lot of that we will unpack. What does it mean? How do we achieve it? But the best part of all that is it's done without any training. I know some of you on the call probably have heard me yapping uncontrollably about inference-time scaling and so on and so forth. I see some faces are smiling here. Well, we actually managed to realize some of that. And what we're going to do today is, we have Isha here, who at a record speed converted all of the stuff into a very nice presentation. She's going to walk us through. She's going to walk us through that. And we have specifically tried making this as accessible as possible. And so there's a couple of things I want to mention before I hand it over to Isha. I posted a link to the website of the paper, where there's an amazing video that she made that you all should see, because it's just it's a very easy way to understand what the method is. And the second link there is of a blog post. So what happened was we were asked to see if we can reproduce R1-like reasoning over a weekend in a small model. And we got some partial success there. And we decided that we'll document every single thing in a live blog, right? In order to sort of give full transparency on what we are doing, how we approach this. At Red Hat, we very much believe in the open source way of doing things. And this is our effort to open that, the same open source door into our research as well. So every day we post results. If you have seen the website, something got done last night where we're showing how we managed to get Generative models to perform reasoning at the level of GPT-4o just by scaling, no training involved. So yeah, please, if you're interested in this topic, please take a look at that website on the blog, comment, interact with us. We would love that. And with that, I want to hand it over to Isha.
Okay, cool. I would like to give a disclaimer in advance that, as many of Akash's team members know, I am coming off the end of a particularly unfortunate case of what I think was the flu, maybe. So if I start coughing in the middle, I sincerely apologize. You should curse the winter illnesses and not me. So thank you everyone for coming out today. Today I'm going to be talking about a topic that is seemingly on the tip of everyone's minds nowadays, which is this promise of inference scaling. And more specifically in this talk, kind of exploring the question of whether or not we can use classical probabilistic inference methods to scale very, very small language models all the way up to an O1 level of reasoning. The very specific technical topic, or the technical title of our talk, is a probabilistic inference approach to inference-time scaling of large language models using particle-based Monte Carlo methods, all of which kind of filters down to an easy slogan, which is particle filtering for inference scaling. So before we kind of dive into the meat of what our method is doing specifically, like Akash said, we're going to kind of keep this high level and kind of try to keep the motivations for why anyone should even care about this as a front runner throughout the entire presentation. So first, we're going to kind of dive into why anyone should even care about open models and why an emphasis on that kind of thing is important. So we all know that closed source frontier models like GPT-4o and Claude Sonnet and Gemini are fantastic at a variety of tasks. So they're good at math and they're good at reasoning, and as middle and high school students across America can attest, it's very good at doing homework and summarizing books you haven't read. It's fantastic at a variety of tasks. But there are several downsides to using these type of frontier models. So the first major one is that they're all kind of hidden away behind an API wall, which requires users to send data to external entities. And this is a problem, first of all, for entire industries like healthcare and education, because in those industries, data is not just as a preference protected, it's legally protected. HIPAA rules and a variety of other regulations do not allow you to send your data to any external entities, which means that unless you are one of a handful of healthcare institutions that is lucky enough to have personal contracts with OpenAI or Google or any of these entities, you're kind of missing out on the power that large language models can provide you in terms of accelerating your entire workflow. But this is also not just a problem for large industries like healthcare. It's also a problem for smaller enterprises that have sensitive data that they don't want to send to entities like OpenAI and Google. So this is kind of, I think, the first problem that everyone kind of mentions with closed source models, which is this idea of an API wall. And coincidentally, as I was looking for graphics for this, there's literally a Malaysian concrete company called API that produces API walls. So do with that information what you will. The second downside of this entire situation is that closed source models are exceedingly expensive to run, both energy-wise and also monetarily. So energy-wise, a lot of small models can be hosted and you can run inference on them with just a handful of GPUs. But very larger models like GPT-4 and Claude Sonnet, these require tens of GPUs. That energy difference really starts to add up once you scale the number of queries that you want to ask. And also, I think what is important to a variety of enterprises and users is this monetary side of things. So this comparison in this table here, which is taken from a website that kind of compares token costs, shows you the first 3 rows of this are the input and output costs per million tokens for closed source models. And the bottom 3 rows are those exact same costs, but for open source models. And you can see kind of the vast gap between how much it would cost users to really make the most out of these models if they're closed source versus open source. Kind of $15 versus 9 cents comparison is kind of staggering. And you can imagine will really add up once you start to like scale up how much you're actually using these models. So this is where we kind of get into this topic of inference scaling. And the kind of basis has been set, which is everyone should care about open source models. And if we can get open source models to perform at a very, very high level, they have a variety of advantages, from privacy reasons and monetary advantages and energy advantages. So let's kind of first dip our toes into this topic of inference scaling. There was a paper that came out from Stanford, seems like a long time ago, but was last year, that shows that smaller, cheaper open models, even at the size of 1 billion parameter models, which when you compare them to the size of ChatGPT and these larger models, is a minuscule size model. When you query them several times for the exact same question, eventually one of those answers will prove to be correct. So you can kind of see on this very aesthetic graph here. The x-axis is the number of samples. So that's the number of times you're actually sampling from a large language model. And the y-axis is coverage at Pascal, which means let's say I sample from a language model 1,000 times. If at least one of those answers is correct, I get a point. So what this graph is really telling you is that although my accuracy for a very small 1 billion parameter model, when I just run every question once, is going to be way worse than a GPT level performance, if I run the same question 1,000 times or 100 times, and I'm able to select the best answer within that, my accuracy can go up tremendously. And so we want to now be able to take advantage of that, right? Because if we know that small models have it in them, somewhere in their sample space, to answer very, very difficult questions, our task is not to improve those models itself, it's to squeeze those answers out of them. So the problem has now become, how can we kind of intelligently navigate the search space of these smaller models to find the best answer that they can provide? And so this kind of captures the problem and promise of inference scaling, which is, as I mentioned, a field that I think lots of people across academia and industry are very excited about, just because of the simplicity of what it offers. Without any external training, just getting small models to perform at much higher levels than initially promised. So I think next we're going to kind of cover the current inference scaling methods and how we're going to grow from those. So the most basic method you can think of in terms of inference scaling, if I asked you to come up with how are you going to kind of use multiple queries to a language model, is this idea of majority voting, right? I am going to put 1,000 queries or 100 queries of a language model, just pick the most common answer. And this, as you can tell in this graph that we got from a Hugging Face blog post, yields pretty good results. The more you sample the model, the higher accuracy it gets in terms of this majority voting type of inference scaling. But again, we can kind of go a little bit more intelligently in terms of how we want to get our answers. So the next step in this is like a best of n type of response. And this is where we introduce this concept of a reward model. So reward models are external language models that off the shelf are trained to take a question and an answer and give you some sort of score based on that. So in best of n inference scaling, I'm going to do the same thing I did before, which is ask a language model a question n times. But now, instead of just choosing whichever one is most common, I'm going to assign a reward score to each of them. And then I'm going to choose the answer that has the highest reward score as my final answer. And then as a combination of these two methods that we've just covered, we have this thing called weighted best of n, where now I'm also going to consider how many times an answer was generated. So let's say I ask a language model a question n times. I'm first going to take all of the n questions and ask the reward model to score all of them, like I did in vanilla best of n. But now I'm also going to multiply the reward score by how many times that answer shows up. So in this like weighted best of n approach, you can see that this yields better results than just a simple like majority voting. And you can kind of see these types of inference scaling curves that everyone has gotten enamored with nowadays. As you increase the number of generations, you increase the number of times you're going to sample your language model, your accuracy is eventually going to go up. But there are more intelligent ways to do this. And now we're going to kind of introduce this concept of a process reward model. Now, anyone who has gone through elementary or middle school has it hammered into them, which is this idea of showing your work is very important. It doesn't necessarily always just matter what your answer is. It matters how you actually got there. You can get a correct answer, but if your reasoning to get there, your reasoning trajectory to get there is incorrect, you should not get as many credits, which, in middle school you can argue with your teacher about. But in the case of trying to get a really strong reasoning model, this reasoning process is important. So we want something to judge a language model's reasoning trajectory over time. So a process reward model kind of addresses this problem, which is it's a language model that's specifically trained in to take a question and a partial answer, so steps of a trajectory, and return a score. So in each of these answers, this is obviously random text, but you can get your score, and you can kind of use this to guide the search to the best possible answer as you generate your partial answers. So you can adjust them according to the scores that you see. It's kind of like getting live feedback as you're reasoning. And so this is a kind of provides a benefit over general reward models, because a process reward model gives you this continuous feedback as you're generating your answer. But let's just remember, the process reward model, like anything else, is it's just a language model. It's not an exact scoring mechanism. So in this big school metaphor that we're using, the process reward model would be a substitute teacher. We kind of trust them. We don't trust them with everything. And so we want to take the process reward model's scores with a grain of salt. And this is where previous methods like beam search kind of falter a bit. So the way that beam search works is you, at every single step, you generate a certain number of candidates, and you use your process reward model to score each of those candidates. Then I'm going to take the top couple, top n, so top 2, top 4, top 8, whatever number of partial steps, and I'm going to remove the others, only focus on those, and continue unrolling those steps. So let's say I generate a couple of, like right here, I generate 5 answers. Let's say A and C, in terms of the step 1 answers, have the highest scores. I'm only going to unroll those, which is a really good idea in terms of trying to guide your reasoning across this path. But, and yes, it generates much better results than best of n or majority voting. So you can kind of see the curve, again, that we're looking for is much, much better in this case. But it can't be optimal, right? Because process reward models are inadequate approximations of the ground truth, which means that they're not going to give you the absolute most correct score in every situation, which means that following this blindly, oh yeah?
Maybe just to kind of build a little bit more intuition here.
Yeah.
On the beam search part, I think everybody here would be very familiar with when, during the school time or graduate school, they were given a difficult math problem. If they go back and look at their workbook, it will look like a beam search. or some sort of a search where I started with a answer and then they were like, doesn't really make sense. I'm gonna start again, or it makes sense up to this point, but then it doesn't make sense. That's the reason I'm mentioning it right now is because that connection to why this thing will look like reasoning will become a lot more clear if we start connecting the dots between these search-based methods and how humans tend to solve math and reasoning problems.
Yeah. So yeah, as Akash mentioned, I think like one of the kind of motivations for why a lot of people are very interested in this step-by-step unfolding process of doing inference scaling is instead of just judging your answer at the very end, like Akash mentioned, the way that humans do reasoning and the way that humans attack math problems is very much an incremental journey. So if you want to do like a show your work type of method, every single step matters, right? So you can make a mistake in your first couple steps and then be like, actually, that doesn't really make a lot of sense. I'm going to go backwards and then explore a different avenue of things. And so the kind of holy grail of reasoning models, especially in these math reasoning problems, is to be able to have a model that is able to generate very like clear, robust steps. And if it does make a mistake, is able to go backwards and self-correct itself. So I think this like very much step-by-step reasoning process is a goal of what inference scaling aims to kind of mimic in this particular way of talking about things.
Isha, there's a question from Eric. Eric, are you able to unmute yourself and speak?
Yeah, you might have to unmute him.
Let me see. Can you try now?
Yeah, can you hear me?
Yeah.
Sweet. I apologize. I was wondering, there was a plot you had there a couple slides ago, that one.
Yeah.
What is the x-axis there?
So the x-axis is the number of generations per problem. So the number of generations per problem is like by the very end of your process, how many full answers have you generated? So if you can see in this beam search kind of tree over here, can you see my cursor? Or
Yeah.
Okay.
Yeah.
So if you kind of follow the path from like right here, A to B to D to B, this is one generation. And then you kind of follow this path over here, this is another generation. And a lot of the inference scaling methods like beam search and also our method unroll answers step by step, which means at the end you have several different candidates. And so the x-axis here kind of covers the number of full candidates that you've ended up unrolling. And so
I got that at the far right, it's 256.
Yeah, so like this right here, so the reason you can kind of see they all start at the same point is because right at the very left end of the axis, this is like one generation per problem. So if I just ask the model once what the accuracy is, this is what you're getting. So this is what all the models are starting with, what all the methods are starting with. And at the very right end of the axis, this is 256 generations. So this kind of alludes back to the kind of like best event approach where like, if you see here, this is literally in a weighted best event approach. You're sampling from the model 256 times. And that's how the accuracy increases.
So on the other one that you just showed, the beam search one, it's 256, but each of those is multiple, like.
Each of those is multiple reasoning steps. So the actual content of your answer doesn't necessarily change. Just the way that you split it up does. So if you ask a language model to answer a question step by step, the way that its response is going to be returned is step one, I don't know, introduce your variable. Step two, do something else mathy. Step three, do something else. So each of those steps is what beam search and then our method plays around with, but at the end, it just is one iteration.
We can also maybe demonstrate a solution at the end.
Yeah.
I'll see if Shiv can pull something and show, because I think that will help clarify Eric's point on like what is the breakdown. In the meantime, you're floated on that.
Yeah. And later on, we're going to cover. There's like one small example of what these like steps kind of mean.
There's another question, Isha, from Sanjeev. Sanjeev, are you able to unmute yourself and ask?
Yeah, can you hear me?
Yes.
Okay, if you're going to cover this later, let me know so we can just defer it. But two basic things. One is, are each of your candidate outputs sort of selected from a per output token basis? Like, do you generate um, n number of output tokens and then pick the most popular or whatever? Or is it, do you select from a collection of output tokens, or what's the granularity of
I think the
output?
short answer is that we'll cover this. Like I think majority of the method is basically based on how do you select it. But yeah, maybe we can so the reward function thing that Isha mentioned, that will play a role, and I think she'll explain exactly how we pick it, because that's a very good point in a sense that is the problem we're trying to solve.
Okay, I'll just mention the second one and maybe you'll cover that as well, which is sort of, is it like the first set of passes are at high temperature and then you kind of reduce temperature over time and things like that?
This is also going to be covered, but I think in a lot of inference scaling methods, because you kind of want that diversity earlier on, you keep a high temperature to allow that diversity and select as you go.
Yeah, it's a very good question. I think you'll like the if you want to jump ahead, I think this in the paper is a very nice blog too, but I'll let Isha cover it first.
These are all great questions. I'm glad people are understanding where we're coming from.
Thank you.
Cool. Any other questions, or should I continue?
I don't have any hands raised, so I think we can continue.
Okay, cool. So yes, so kind of we've covered this topic of beam search and how they kind of blindly follow these process reward models. The process reward model tells you, okay, listen, this step one and this step one, these two generations you did, these are giving me the highest rewards. I'm only going to follow those. This is not necessarily always a good thing because, as I mentioned before, process reward models are not like perfect approximations of your data set. They're not perfect approximations of the ground truth, which means that following these process reward models blindly to determine which answers you want to continue expanding and which ones you don't leads to this thing called reward hacking, which means your final outputs are optimized to score really well according to this like nice little reward model you have. But the reward model's approval is not what you want, right? You want your actual data set to have a very high accuracy. So reward hacking kind of leads to this problem where your final output has a very high reward score, but doesn't necessarily always translate to high accuracy on the actual data set you're testing. So this is where our method comes into play.
Do you want to maybe expand a little bit more? Like, so
yeah.
on why the reward models are inaccurate, or why is the notion of accuracy there, right? So specifically for math problems, as we know, a reward function, as he has said earlier, right? It's basically just another language model that has been specifically trained to figure out whether a step is correct or incorrect. But it is nevertheless a trained model. It is not a symbolic verifier or some kind of like a ground truth, right? And that's where the notion of accuracy comes from. That it is much better than an average model or an average person on judging the quality of the step in terms of its accuracy, but it is not perfect.
Yeah. And if I had a reward model that was perfect, then a lot of these methods are not even really necessary, right? Because if I have a 100% correct verifier reward model that's kind of looking over my shoulder as I'm solving this problem, that can tell me, okay, step one, yes, you got this correct, move on. Step two, yes, you got this correct, move on. Step three, nope, that's not right, go backwards. If I have an exact verifier that's monitoring my progress as I continue through my reasoning trajectory, then that would be perfect. But this is unfortunately not an ideal situation, and the process reward models are not exactly correlated with whether or not a reasoning step is correct. The other side of things is that reward models and reasoning steps are kind of, they're subjective. So especially in mathematical reasoning, whether one first step to a math problem is significantly better than a second one is not always super clear. And so having a reward model that gives you these scores and then blindly following them can have some consequences later on. Because again, like Akash mentioned, it's not a perfect approximation of math or reasoning or whatever you're trying to solve. Yeah. So this is where our method comes into play. Please enjoy this very cute little graphic I have of our particles. The technical topic and the technical title of our talk, as I mentioned before, is a probabilistic inference approach to inference-time scaling using particle-based Monte Carlo methods. But in general, in overall, this is just particle filtering for inference scaling. We have a very complicated looking algorithm, but for the purposes of this talk, we're going to cover it in a kind of high level, hopefully easy to understand method. So let's start with an example. I feel like this is the best way to kind of unpack how this actually works. So ignore the political question, but let's say we have a math question that is a Senate committee has 8 Republicans and 6 Democrats. How many ways can we form a subcommittee of 5 members that has at least 1 member from each party? This is a math question that, it appears on math contests across America. And the way that we're going to approach this in our method is first we're going to do something, and we're going to initialize n particles. And you can kind of think of each of these particles as a new person that's kind of involved in this collaboration. So we keep, as I think someone mentioned earlier in one of their questions, a relatively high model temperature. So a temperature of a model controls like how creative or random these generations are going to be, which means that if I have a very, very low temperature for my model, and I ask it the same thing 5 times, it's going to give me 5 very, very similar responses. But if I have a higher model temperature, closer to 1, then that means that if I ask the model the same question 5 times, it's going to give me relatively different answers. And so when we're trying to do inference scaling and we're trying to explore the search space as much as possible, we do want to keep a higher temperature to allow this kind of diversity and creativity in the exploration. So each particle, as I mentioned, you can kind of think of a new person that's involved in this collaboration, and each particle is going to contain the contents of a reasoning trajectory so far. So the first step is each particle is going to take a step. And what a step means in this process is the text that a language model generates until it hits the double \n delimiter. And for people who are not familiar with that, a double \n is literally just like a new line. So when a language model will answer a question, like this math question, it'll say step 1, blah, 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 new line, blank. Step 2, a bunch of words, new line. Step 3, new line. And so kind of breaking up this answer with the double \n delimiter means that you can break up reasoning in that way. And so each of those steps, this is kind of alluding to what someone else was asking, it's not necessarily unrolled on a token by token level. You're choosing steps in terms of like entire chunks of reasoning. So let's say in the very first iteration of this process, I ask the language model this question 4 times, and I ask it to generate the first step. So now I have 4 particles with 4 different first steps of answers to this question. The next thing I'm going to do is I'm going to take this process reward model that we've been talking so much about, and I'm going to assign a score to each question and partial answer. So I take the question, I take the partial answer, I feed it to the reward model, and the reward model is going to throw me back a score. So in this case, it assigns a score of 0.849, all these things. And each of these scores correlates to how good the reward model thinks this exact step of reasoning is. The next thing I'm going to do is I'm going to softmax the reward scores to get probabilities. So if anyone's not familiar, softmax is just a function that takes in a set of numbers and converts it all to like a set of probabilities. So you can kind of see going back and forth between these 2 particles, 1 and 4, had relatively higher scores. And so they get converted to relatively higher probabilities. And what these probabilities actually mean in our process is they represent the chance that each of these particles will be chosen, will be evolved in the next step of this process. So you kind of draw a distinction here between what our method is doing and what previous methods do, where previous methods would literally just have taken this score. They only would have evolved this particle. But in our method, we are converting the scores to a set of probabilities. And a particle that has a lower score does have a lower chance of being evolved. But the evolution process is determined by sampling and not just choosing the like argmax, the highest particle score. So the next step of this is we're going to do a resampling, which means that each of these particles in the next step of this process are independently resampled from the previous ones. So this is the first particle of our second step. This has a 30% chance of being evolved from this particle, an 18% chance of being evolved from this particle, a 17% chance of being evolved from this particle, and a 34% chance of being evolved from this particle. So let's say randomly, it's a completely independent random process. This particle happens to choose this one, this particle happens to choose this one, and these two particles happen to choose this answer. So that means that this particle 4 here, is going to continue its next steps, starting from the contents of this particle, step 1. So to avoid kind of saying this particle 1,500 times, just to give you an example, you can kind of see here that because both particle 3 and particle 4 were evolved from the same particle in the previous step, their first, up till here, step 1 contents are the same. So that kind of alludes to the fact that like your step 1 contents get passed on, and then you ask the language model, given what I have so far, generate the next step of reasoning. And so you do this entire thing a bunch of times where each particle in your process generates its next step of reasoning. You use your process reward model to calculate a score, judging how good that reasoning trajectory is. You convert that score to a weight with your softmax, and then you resample the particles according to those weights. And then you just do this again and again and again until all of your particles have generated completed trajectories. So this is kind of more, yeah.
I want to interject here because I think this question has come up before in a conversation. When Isha says they are sampled randomly, it doesn't really mean like it is sort of sampled from a uniform distribution. I think what she's trying to imply here is that we're looking at the distribution of the reward model, and we're sampling from that distribution. We're not sampling. So whenever we heard the word random, replace it by sample from the reward model distribution.
Yeah, and just to kind of underline that, you're sampling from the previous set of particles with the set of weights that the reward model gives you. So if the reward model determines that these two happen to have higher scores, then they have higher probabilities of being resampled. So yeah, you're resampling from.
We have a question from Nick. You're on mute yourself, Nick.
Yeah, just a quick. Maybe you're going to cover this, but are you then? Is this just one path, or are you doing a beam search at this level as well?
So you do this so the set of particles that you're maintaining, those particles are the ones that kind of keep the trajectories. It's like each particle here. So this is like in a much later slide, but you can kind of see here, this is what, ignore the particle Gibbs title, but you can kind of see here, like eventually this is what a trajectory of this would kind of look like, where a particle has a step 1 here, then you get a step 2 here, a step 3 here. So the trajectories are kind of determined by.
Nick, just to connect the dots here, this is basically a sequential Monte Carlo method family. So that think of it like probabilistic beam search. The beam search is very deterministic and kind of like
right.
in this context very naive. But this is essentially saying, as Isha mentioned earlier, that beam search has an inherent assumption that the reward function is perfect. So it just trusts the mode, right? What the point here is that trusting the mode is a fallacy if the reward function isn't perfect. And so the propagating that uncertainty that the reward function actually has, it's not sure, is why this becomes a probabilistic version of the search. And why we are able to avoid reward hacking that Isha alluded to earlier.
Cool, thank you.
Yeah, of course. So yeah, this is kind of the overall process that this particle filtering for inference scaling method goes through. So just to kind of hit the nail on the head one more time, you have your language model, and for each of the particles, you generate your first step of reasoning. Then you take your process reward model, you score each of those steps, you convert that score to a weight or the probability that that particle is going to be resampled, and then in the next step, you resample your particles. And then each of the particles inherits the previous step 1 of the particle that it evolved from. You generate a step 2 based on that. And by the end, you kind of have this process where it's similar to beam search, but you have at every step, instead of just taking the highest possible reward score, you end up sampling with probabilities that the reward score gives you. So this kind of this allows you to balance exploration and kind of exploring as many different answers in as many different reasoning trajectories as you can, while also exploiting the benefits that the process reward model can give you. And yeah, if there's no questions about the method itself, I will touch on some of the results. We do get some very cool numbers, as the excitement that everyone has been talking about this project can kind of allude to. The first kind of 3 statistics that I'm going to touch on. The first one is that this method gets.
Yeah, I just want to highlight we're not able to see our method's results on the last row is not visible, so you might want to have to move it a little bit around. Yeah, there
this
you go.
entire
Now
time
it
it
is.
wasn't zoomed in. That's so sad. Okay, sorry. Yes, this is like the most, I think, buzzworthy / important statistic here, which is that with a Quen 2.5 math 7B model, so like a 7 billion parameter model, which in the context of large models like 4.0 and 0.1 is minuscule, we're actually able to match the accuracy that 0.1 provides on this data set. So I think this is actually a lot more.
I'm gonna take like at least 3 minutes to explain that result, why it is important. So 0.1, if you don't know, is the first reasoning model that came out, right? So when people say R1 is great, it's because R1 is an open source reproduction of 0.1. 0.1 was from OpenAI. It breaks all benchmarks on basically everything prior to it. So just I'm gonna leave. I think it's worth going through this slide because there is so much to unpack here. As you can see, the GPT-4o is not even an issue. I think there's a result not listed here, but if you go to our blog, we actually found yesterday that just by inference scaling, the Granite 8B model, the one that we productize in InstructLab, we're able to beat GPT-4o on both math and AMI. So yeah, I mean, Isha, maybe like we go through like this result a little bit more in detail. Yeah.
Yeah, I was going to cover it more, I feel like the plots actually give you a little bit more of a visual understanding of like how tremendous the results are. So I'll go back and forth between the plots and the table, but just to kind of give you like a visual understanding of how staggering some of these results are. The accuracy of a Llama 3.2 1B instruct model hovers around like 22-23%. So this is all the way like at the bottom of this plot here. And the Llama 8B model accuracy is around 42, 70B goes all the way to like 65, and GPT-4o touches here. You can kind of see that with only like a few model generations ranging from like 1 to 128, you're able to get such a staggering improvement with literally nothing else except intelligently navigating your search space. So this is like significantly better than the weighted best of n results, significantly better than DBTS and other search method results. And you're able to get from a 1B model almost to the level of like a 7DB model with 128 generations. And you can kind of continue this trajectory with an 8B model where with an only 8 billion parameter model and literally no additional training at all, and this is not even like a math instruction tune model, you're almost able to reach a GPT-4o level of reasoning. And like Akash mentioned, this is like kind of a very staggering result because the size, the complexity, the expensive nature of the GPT-4 model, and the amount of reasoning that it's able to provide you to be able to get that and unlock that from literally just an 8B model, I think is kind of incredible. And only with like 32 generations are you able to kind of unlock that result. And then again, to like hit the nail on the head with how great some of these results are, you want to start with this 1.5B instruct model. You're able to get from, the 7B instruct model, you're able to get from this type of accuracy all the way to 0.1 preview, which, as Akash mentioned, is kind of the talk of the town in terms of how it's able to actually capture what seems like human-like reasoning results. So 0.1 type reasoning thinks step by step. It kind of goes through what one would think a human type of reasoning looks like on a math result. And we're able to get that with an open source model and no additional training whatsoever. And that kind of tells you that the performance that a lot of these closed source models have are hidden away somewhere in open source models. You just need methods like the particle filtering approach that we provide and other inference scaling approaches to unlock and really just squeeze the juice out of a lot of these open source models.
There's a question from Eric. Eric, you want to unmute yourself?
Yeah. I guess you already answered it. I was just trying to clarify there what your x-axis was.
Yeah, so the x-axis is the kind of same as the previous graphs. So this is like the number of total model generations that you have accomplished. So in this case, this is like the number of particles. Oh, sorry, my sister is calling me. This is the number of particles that you have. So in this case, this is 2 particles, this is 4 particles, this is 8 particles. And again, in our case, a particle captures a full reasoning trajectory. So by the end of the particle filtering process, each particle will contain a full trajectory from start to finish, at like every step all put together. So the x-axis here on all of the graphs is the number of particles that you end up unrolling. So this is just, you can think of this in terms of like the best event approach, in terms of the number of times you ask a language model to answer your question. And the fact that you're able to get from, this accuracy all the way up to an O1 accuracy with 32 generations, if you think of that cost-wise, that's insane. The cost that like a 7B model has to run versus the cost that O1 takes to run, you can't even really compare them. So I think, the scale of how well this method works really kind of alludes to the power of inference scaling and the simplicity that the method provides.
And it would be cool.
You earlier had a question about like, how many generations. So like, and I think you also posted it in the chat. A lot of these generations, even though they're, say here, they're 32 generation, first of all, like 32 7B calls is like way cheaper than even one single call of O1. However, a lot of the answers, as we showed in these steps, have a lot of overlappings with the other particles, right? So the net number of new tokens generated is actually fairly low, right? Because of the way prefix caching works in VLM, and I'm hoping I see Nick, so probably some other folks here, they want to chime in on how that, like the actual cost is not real 32 generations.
Yeah, I mean, I was interested if you could take, the x-axis is using here and turn it into somehow cost.
So
Yeah.
there's actually a work that I can maybe send to you but the chart that Isha earlier showed where, so we did some comparisons and it's like, I think this comparison is like, I think 6 months old or 4 months old, it's like third of the cost, probably less, but not for the O1 model. So O1 model is like way more expensive. And so we don't really have an estimate, but there's a paper that does convert it to flops as well.
Maybe another thing to note here is also like compared to the other inference scaling method, like we here beat, so the best score you get from DBTS, which is running 128 times, we beat that with just 8 model calls here.
Yeah, I think that's probably a very good point too. I don't know if Isha, you want to touch upon that, just comparing the efficiency of these methods.
Yeah. So I think like the kind of 3 things that I think are kind of staggering about this. Number 1 is the accuracy, but I think the second thing is also the speed at which, as Shiva mentioned, you get to these results. So the scaling rate is also very important when you think of inference scaling, right? Like all of these curves that we've been looking at in the presentation so far, what matters is not just how much you can increase the model, your model accuracy, but also how fast you can get there. And I think one of the really cool attributes of this model, of this approach, is that because we're kind of balancing, because it's a probabilistic method and you're kind of balancing the exploration and the exploitation, that kind of trade-off that we're making allows us to get to like the same accuracies that competitor methods are getting, but way, way faster. So, you're able to get to a 50% accuracy that DBTS gets here, and we're able to get it in only 8 model calls. You look kind of here, the same accuracy that a DBTS method gets in 128 model calls, we're able to get between 4 and 8. So the speed of improvement, I think, is also really important to note. And I think is one of the benefits of this, because it's not just about the accuracy you're getting, it's about how quickly you can actually get there. And I think the rate at which these methods end up scaling is also like a significant benefit of this method that we provide. Yeah. Sorry. Yeah, so I kind of wanted to touch on why you should actually care, because I feel like there's a lot of MET papers that come out nowadays that touch on the topic of inference scaling. It's kind of on everyone's minds, but why should you actually care about this method and its results? You do, as we mentioned, and not to overextend it, but you do all of this scaling small models to very, very high numbers without training anything at all. So there's a lot of papers that have come out recently that do similar things where they will get a small model to be at large model accuracy, but they're actually training on trajectories. They're training on the results of larger models. They're training on hand-curated data. And this method doesn't require any of that. And I think that lack of training and the fact that you're literally just taking an off-the-shelf small model and an off-the-shelf reward model, putting them together and allowing them to work together to squeeze a lot of performance is really, really cool. So you're just allowing it to kind of discover its potential just by navigating the search space. So you kind of skip the entire training process of this, and you literally just get there by querying and searching the model with a lot of efficiency. And in terms of why you should care, kind of tying this back to the power of open source models, if you follow results like the ones we've shown you today, you have a way to use small open source models to get the applications and to get the capabilities that you want for a variety of different domains, right? It's not just about math reasoning on a math data set. If you can kind of apply this to your own domain or the domains that enterprises use or users have in their applications, you can get very, very strong results, all while keeping your data secure and not having to send it to external parties and keeping costs way down. And then, tying in things like InstructLab, allowing yourselves to use small customizable models that can really help you use the power of open source models for your own domains. And I think there's a lot of cool things you can do for the future. So as Akash mentioned, using VLLM to optimize this and make it cheaper, and kind of reduce the cost and the time that inference time scaling takes. And then also, Akash will mention this later in terms of how you can use this to make an R1 style model over the course of a weekend. But using these trajectories that we've generated from this entire particle filtering process, can you then train on those to make your models better at reasoning inherently? There's a lot to do here that extends even beyond the promise of inference scaling. So yeah, that's kind of what I have for you. There's a really cool website that I think explains this entire method very intuitively and has more details if you want more of the math and robustness in this website here. And yeah, feel free to reach out to any of us with any questions. Thank you so much for your time. Any questions that I can answer?
I noticed you spent a lot of time kind of like on the math reasoning benchmarks.
Yeah.
Like, I'm going to do my usual pitch about your average Red Hat customer probably is more interested in like how it can answer, my insurance policy questions.
Yeah.
Yeah,
Like,
so I think I'm gonna send this link to you I'm gonna paste it in the thing. So it'd be really good if so people who are interested in how this work that we just presented goes into creating general reasoning models. Please go see there. We're putting everything that we're doing every day there, and it precisely answers that question. So the very cool thing we found is if you train the model, and we'll get into how we train probably in another talk, on the data that this method generates inference scaling, then on math, that reasoning transfer to everything else. And by the way, we did that on Granite, and we found that on our specific InstructLab use case of RAG, the model can reason through your document and has achieved the best results we've ever seen, rivaling those, beating every R1 distilled model and coming very, very, very close, almost like the same exact score with R1 on RAG, even though it's never. So there's a lot of transfer that happens. But if you're interested in that one, I would really recommend to go check this blog out. Joe, you have your hand up.
Yeah, on the earlier chart, so there was another benchmark, the AIME benchmark that 01 scores really high on, but the inference scaling doesn't converge on that as quickly.
Yeah.
Any explanation why? You should
I think there's a couple, and Akash can mention this earlier, but I think the first one is just that it's like a very, very difficult data set. And I think that sometimes it takes, slightly higher powered things. But I think Akash mentioned that we recently got results on Granite that matched something on Amy. So
GPT-4, oh, not GPT-4. But
Oh.
I'm gonna let me just I'll take over the sharing if you don't mind. One second, Isha, just quickly to demonstrate this result. That as you just said, like Joe, this is one of the hardest. It's like Anisha is probably the right person to talk about it because she, if I'm right, she's like used to do a lot of math Olympiad and was very good at it. But basically, those are math Olympiad questions. However, yesterday, and by the way, guys, this is the blog post. Please go see what we're doing here on the daily. Yesterday's update, for those who didn't miss, was we basically done every single experiment we have done so far. And Joe, this is what I wanted to highlight. On Amy, we did get to reach here. And if we sample 8, we can actually get to, and this is with the 5.4 model, which is a 14 billion parameter model compared to the O1. Right? So we're getting there step by step, but yeah, I think this is very, very competitive. I mean, this is like mind-blowingly good, if you will. The other thing I wanted to highlight is Amy. We actually managed to get Llama to get to a 20 from the original 10 accuracy on the same Amy benchmark. And Amy is only like less than 30 questions, but they're super, super hard. That's why, but we're very proud of this number because I think these numbers are actually better than, or they match the number that Llama distilled R1 model that they created gets. And in full transparency, we are using data that other groups like this one from Stanford is creating. But yeah, this is sort of like I said, open. We're sort of we've opened up our shop. Everybody can come peek in, see, and tell us at the bottom.
Yeah, and maybe I can help explain that folks who may not be aware, right? So this represents research that Isha, Kash, and our whole research team have been doing for the last several months, right? The 2 papers that were just published literally this week, kind of are the result of that. And then what those what was the name of the conference that you published those for, Akash? The iClear, right?
I'm not gonna. I just learned I'm not supposed to say the name of the conference by part of the rule.
Oh, okay.
So let's not say the name.
For an upcoming conference, so it's early research, right? But like the hope here is that it it eventually makes its way into capabilities in product that that we can bring to customers. By the way, that it's one of the hottest areas of research, inference scaling or test time scaling. Like it's not just us doing work in this area, it's other researchers. And then it came into the public's attention last week when the DeepSeek launch came out, right? And people started seeing like the impact of like what reasoning could really mean from a consumer model perspective. But I think there's a lot more we can do here. And then this blog that Akash was showing. So I challenged Akash to like, can we get this stuff out there? Because like these papers are great, but man, like I spent last weekend trying to read Akash and Isha's paper, and if it wasn't for GPT-4 and helping me a lot, I would not have been able to get through them. So being able to sort of distill those down into talks like this, into blogs like what Akash showed, and get that research just out there, right? I think as a company, we need to continuously establish our credibility in the AI space. We're not a known commodity. Obviously, IBM is more known. They've been doing AI for longer, but we want to establish Red Hat, both here on training, on inference scaling, on inference itself, VLM model optimization. So this blog and other stuff like it is what we're trying to also bring out more forcefully to redhat.com. So you'll see us finding forums to actually share this work, but it's not something that's going to go into a product tomorrow. We hope to actually show product potential around this area by Summit and so forth. And then obviously there's more work to be done. So hopefully that makes sense.
Thanks, Joe. We'll hang around for like a 5 minute or so for questions. Just maybe unmute yourself and we can just take it and then. Yeah, go ahead, Tom.
I'm curious about the reward models. So just check if I understand it correctly. So is it right to say that rather than focusing on fine-tuning a model to compete with the bigger, rather than fine-tuning a small model to compete with bigger models, what we have to do is to select the correct reward model? Or is it a matter of like there's going to be a bunch of reward models to select from that are sort of pre-created, or do we have to, would customers, I mean, have to train and fine-tune their own reward models to make it work for their use case?
So I'm gonna maybe answer this in two parts, and then Isha, you can chime in. So there are two dominant directions that the industry is following right now. So first one obviously is purely inference scaling. Because smaller models are very cheap. Even if you make 30 calls on them, it basically barely makes a dent. But the question that you asked, Tom, is about, well, do you need reward models? Yeah. So you will, if you're only relying on inference scaling, you will need domain-specific reward models, right? And I in the chat I pasted, and this is the point that Joe was mentioning. There are two papers that went down. The first one obviously is this. The second was about how do you create a reward model by leveraging pre-trained language models without any human annotation data. It's actually a pretty good paper, definitely worth a read. But that is a limitation. So in some manner of saying, the way R1 and O1 was created was, and this is an oversimplification, this is not how it was done, but the idea was, okay, I know this model, and this is something Isha kept saying in the talk as well. These models, I know these models are capable of generating the correct answer, right? So can I pull that answer out? Turns out inference scaling will help you pull that answer out. But now you have that data. And one thing we know, at least here at InstructLab, is that if the data can be there, I will train on it and bake that capability in, right? So I realized, well, inference scaling can make my model reason. Can I train on that reasoning data? And that's basically the principle behind reasoning models, even in R1 and so on. But and what I was alluding to in my comment about what we found is training on reasoning data from the domain of math automatically makes it reason on everything. I mean, one thing we tested was rack performance, which just shot up, almost unprecedented. I think we'll share some more details on. I'm looking at Abhishek because that he ran most of those experiments. We'll share some details on that. Probably today, dump it on the blog post to show like why what happens, why this transfer happens. So yeah, Isha, do you want to add something to it?
I think that pretty much covers it. I feel like one of the limitations of the approach is that you do need a reward model to help guide your search. And so I think if you're looking for applications that are more customized to specific domain interests that customers have, you do need a reward model that is somewhat able to guide that search. And so that can either lead to training your own reward model or, as Akash mentioned, training on the actual trajectories and hoping for a better reasoning approach. But I think you covered it.
Thanks.
All right, go next.
Hey, so I know as far as like reasoning tasks go, like the major evaluations that we typically do are like math, AME. For when it comes to like general reasoning though, like what needs to be developed in order to evaluate how well the models are actually reasoning? Because we can look at like the answer, but kind of as we pointed out, the steps taken to actually get to the answer are important as well.
I think it's like a much more complicated. Like I feel like the reason that people focus on math and other types of those specific reasoning benchmarks is because they are a lot easier to evaluate. So I think there are more general reasoning benchmarks, so you can test like final answers, but a lot of those do require like a language model as a judge to determine scores. So I think it's a little bit more challenging, and it's kind of why a lot of math things are in focus.
I think it's kind of I'm gonna basically like say the same thing I said earlier. If you are able to train on the math reasoning, it generalized. So the answer is you don't need it if that's the route you're going with. You don't need specialized domain specialized models, reward models, because training on think of it as a skill set of you're building a skill set of reasoning that transfers, right? And that we have seen in the experiment that you have been part of. What I think his point is, if you are only going to rely on inference scaling, then you will need domain-specific models. But I just want to make that clarity, sort of like why the interest in inference scaling, and it's not technically a limitation, is ultimately you would want to bake that into that reasoning ability, the skill set, into the model. Right. Nikhil has a question from the.
So is the reward model a language model? And if it is, can you directly use the reward model to generate the answer?
It is a reward model is a language model. It's a very small model, and it's trained to score, not generate. So because the reason I think is like it's a good question, but let me answer, because the question could be, but why is it able to judge? Well, judging whether something is correct or incorrect is a classification task, right? Drawing a boundary, which is orders of magnitude easier than generating the answer. So that's a good question. Okay.
So yeah, so both the models may not be as strong as maybe a big model,
Correct.
but they can still match the performance in combination.
Yeah, and because of that, I think that what we are proposing in the work is that a probabilistic approach is a better one, because neither of the model is perfect. Right. William, and maybe we can take this last question and then.
Yep. So if I look at this as a 3 or 4 step training, like the normal, let's say, two step training that we do, then you run this through this process to capture that new data set, retrain with that data set, that resulting model, will that still need that inferencing time part, or it will do the reasoning on its own without additional help? Trying to understand if doing that 3-step leads to not requiring this, or I misunderstood.
So I think if you have trained the model, it will get to start doing reasoning. But you can take any model and apply inference scaling to it. So for example, when the R1 models came out, we took the Llama R1 distilled Llama model and ran a particular version of our method on that, and we showed that we can further improve that model's accuracy. So it's compositional. Like you can apply inference scaling on any model, hence also to the model output, because it's basically a search strategy, right? The better the model is, the better it can search. The better coverage it gets, and then you are tapering it down to the right search level. But of course, you see saturation happening. So the improvement you will get is lesser than what you would get by applying it on the base model.
One more question. I did not see it. What type of latency does this type of reasoning inject? Is that a constant? Is that variable based on the type of reasoning it's doing at a particular moment?
So on the reasoning side, I'm assuming you're asking, like, okay, we took this data and we trained the model. What kind of latency do we see? Well, so I mean, a very good estimate will be running a question on R1, and you will see the latency. And by latency, I'm assuming you mean like the time it takes to generate the final answer.
Yeah.
Right. Okay. Yeah. So I think it's on the same order of magnitude, like, because now your average generation length has gone drastically up, right? So it does go up. So I wouldn't call it latency, because the model starts generating right away, and latency has a particular meaning in the context of inference. So I don't want to conflate the two terms. It's that the average generation length goes higher.
Good point. Thank you very much.
Awesome. Hey, thank you very much, Isha, for staying 10 minutes after the call. And thank you so much, everybody, for joining and asking awesome questions. I really, really liked it. Again, please join us in our journey on the blog post. If you have any other questions, feel free to reach out. We're working on this every day. One last thing. Next week, speaker, we'll actually make some changes in the schedule, but we have one of the original founders of co-founders of Open Devin project, who will be joining us to talk about agents and his work on, like, how they have managed to do this in the open source. So definitely join. I'll send the details. It will be at 10:30 instead of 11:30, but I'll send the details out.
Thanks again.